Hi everyone, this is Tasaki. In this short video, I like to discuss the essence of our new paper with this title. So I'm going to explain you the difference between odd and even. And as you see, this is about quantum spin chains, and it's also related to Haldane phenomena and also to symmetry protected topological phases. So if you want to learn basics of this field, I recommend you to read my book, which was published like 2 years ago, and I think this is well written. Okay, so let's get back to this talk. So this is a joint work with Daisuke Maekawa, who used to be my student. And actually, this is based on Daisuke's senior research project. Here, senior doesn't mean an old person like me. Senior means a fourth year undergraduate student. Okay, anyway, let's get started. So I start from motivation. So let's go back to the very famous discovery by Haldane, which brought him the Nobel Prize, probably the 2016 Nobel Prize in Physics. So let's take a look at the spin S quantum antiferromagnetic Heisenberg chain with this Hamiltonian. The only parameter is this spin quantum number S. Then Haldane discovered that the ground state of this Hamiltonian is critical in the sense that it's unique and gapless if S is a half-odd integer, but it's disordered in the sense that it's unique and gapped if S is an integer. So this is a very drastic qualitative difference, and everybody was surprised in this 1980s. And now there are several theoretical explanations for this difference, but one simple and intuitive diagrammatic explanation is provided by something called the valence bond picture. So what is this? Well, by a valence bond, I mean a spin singlet formed by two spin 1/2s. So this is spin 1/2, this is spin 1/2. In this talk, a black dot always represents a spin 1/2. And this is familiar up, down, minus, down, up state. Usually you divide this by square root 2 to normalize, but here I'm using a normalized spin singlet. And then you ask, can you form a translation invariant state of a spin S chain by using this spin singlet, short-range valence bond spin singlet? And if you consider spin 1, the answer is yes. OK, what is this? Well, I want to construct the state of a spin 1 chain. So we want a spin 1, but as you learned in quantum mechanics class, by preparing two spin 1/2s and projecting it onto the symmetric sector, you get a spin 1 state. So here, this is a single site. You have two spin 1/2s on this single site, and you symmetrize. And then you get a state, spin 1 state. Here also you have a spin 1 state, spin 1 state. And they are sort of connected by a valence bond, spin singlets. So the answer is yes, you can form a state like this. And for spin 2, yes, in this case, you want to have 4 spin 1/2s on each side, and you can do like this. Okay, so the answer is yes for integer spins. What about spin 3/2? Now you want to form spin 3/2. So it means that you need 3 spin 1/2s on each side. And then you, of course, you get a state with spin 3/2. That's OK. But in this case, you have to locate spin singlet like this or like this. And you can never have a translation invariant state. So in this case, the answer is no. And the answer, this is the same for other integer spins and other half-odd integer spins. OK. Now, this picture is closely related to a model called the AKLT model. And it's an artificial model, but it's believed that it is qualitatively similar to the antiferromagnetic Heisenberg chain. And this is the Hamiltonian. It's written in terms of the projection operator, but I'm not going into detail. But anyway, it's rigorously known to have a unique gap ground state. It's been proved. And for S = 1 case, it was proved in this original paper. And for general S, the existence of gap is proved in this very famous paper for MPS, matrix product states. OK. And also, the exact ground state of this Hamiltonian is known, and it's called the AKLT state or the VBS state. The VBS stands for valence-bond-solid. Valence bond is forming a solid like this, and it's the state I talked about in the previous slide. Okay, so in equation, it's like this, but again, I'm not going into details. If you're interested, go to my book or read the present paper. Okay, so this is for spin 1, this is for spin 2. These are the AKLT or the VBS state. Okay, so that was about the qualitative difference between integer and half-odd integer spins. In 1992, Masaki Yoshikawa discovered further qualitative difference. He examined something called hidden antiferromagnetic order, and he found that there is a qualitative difference between the AKLT states with even S and odd S. So this was a surprise to us, and this had been a mystery for a while, but it was finally resolved in 2009 when the theory of symmetry protected topological phases, SPT phases, was developed. And it was done by Gu Wen and also Pullman, Turner, Belk, and Masaki Yoshikawa himself. So now there is a rigorous theory by Yoshiko Ogata, and everything is almost completely understood. So what are we going to do in this paper? Here, we want to provide an intuitive diagrammatic explanation for this difference. So as for the difference between integer and half-odd integer, this valence bond picture gave us intuitive diagrammatic explanation. So we want to do the same thing for this difference between even and odd S. Okay, so but before going on, I want to say something about SPT phases. Okay, so let's consider a quantum spin chain with some fixed spin quantum number S. And let M be the big, huge space of Hamiltonians with a unique gap ground state, disordered ground state. And take arbitrary two Hamiltonians, H0 and H1 from this big space. And we say that these two Hamiltonians are connected if there exists a continuous family path H of S within this M. So every HS has a unique gap ground state where S runs between 0 and 1. So this HS interpolates between H0 and H1. In this case, we say that these two Hamiltonians are connected, very natural definition. And there is a conjecture by Chenggu and Wen that all Hamiltonians in this big space M are connected. In other words, there is only one phase in M. Okay, that's kind of boring. But if we impose some symmetry, the story changes drastically. So let M sigma be the subspace of M with Hamiltonians, which consists of Hamiltonians which have some symmetry sigma, like the time reversal symmetry, okay, or inversion symmetry. And take again two arbitrary Hamiltonians from M sigma, and we say that they are connected if, again, there is a continuous path within this M sigma, connecting these two things. And now with this definition, this M sigma may consist of distinct connected components. It's different from here. And in this, if this is the case, we say that these are symmetry protected topological phases. These connected components are different SPT phases. Here is a very rough picture. So suppose that this whole three-dimensional space is this space M of Hamiltonians with a disordered ground state, a unique gap ground state. But except for this circle. On this circle, I suppose that we have Hamiltonians with gapless excitation. So this does not belong to M. But all this three-dimensional space, except for this circle, belongs to M. And suppose that our H0 is here, H1 is here, and of course they are connected within M. So M consists of a single phase. Next, suppose that this M sigma, this plane here, this two-dimensional plane is M sigma, this space of Hamiltonians with certain symmetry. And in this case, now you cannot go from H0 to H1 within this plane because here is a circle of gapless models. So this circle does not belong to M, or it does not belong to M sigma. So in this case, this M sigma, the plane is divided into two regions, two phases. So in this case, we have one SPT phase here and the other SPT phase outside here. So without symmetry, everything is connected and everything is in a single phase. But with this symmetry restriction, we get this phase structure. So this is SPT phase. Okay, so as for quantum spin chains with integer s, everything is well understood. And basic physical understanding was given by Gu Wen, Pullman, Turner, Belk, and Yoshikawa, and Yoshiko Ogata provided mathematically completely rigorous theory. And now theorem is that when this sigma is the bond center inversion symmetry, you just flip, or the time reversal symmetry, or the Z2 cross Z2 symmetry. This is simply the pi rotations about the 3 spin axis. So if sigma is one of these 3 symmetries, then M sigma consists of at least 2 SPT phases. Okay, and one of these phases contains this trivial Hamiltonian. This is very trivial. It's simply the sum of SZ squared. And so its ground state, of course, disorder is this state, which I call the 0 state. It's just a simple tensor product of 0 states. Okay, so this belongs to a trivial phase. What about the HAKLT? Okay, HAKLT Hamiltonian belongs to this. Again, this depends on actually the parity of S. This belongs to a non-trivial SPT phase when S is odd, 1, 3, 5. But if it belongs to the trivial phase, like this one, when S is even. So this is the essence of the difference between odd and even S that we wanted to understand. So the goal of this paper is to provide an intuitive diagrammatic explanation of this difference here. Okay. So, and here's the advertisement. So if you're interested in symmetry-protected topological phases in quantum spin chains, it's very interesting. And I recommend you to take a look at my online lecture video with this title. And I will make a link from this video to this one at the end of this video. So wait until the end. Okay, now I want to explain what we have done in the present paper. I'm going to define something that we call the asymmetric VBS states, the asymmetric valence-bond-solid states. So I start with the asymmetric valence bond, which is the building block. And this is very simple. This is a state that consists of 2 spin 1/2s, like spin singlet. Well, it's actually almost a spin singlet, but this with new parameter mu, which runs between 0 and 1. So when this is 1, this is just a spin singlet. When mu equals 0, it's just up-down. Okay, so it's not symmetric. It changes when if we switch P and Q. So I express this state diagrammatically like this with a segment with an arrow. Okay, so when mu equals not 1, this state is clearly not invariant under inversion, switching P and Q. And you also easily find that it's not invariant under time reversal or the Z2 cross Z2 transformation. I'm not going to explain details. Please take a look at our paper if you're interested. So anyway, this is a building block and it's not symmetric. It's not invariant under these 3 transformations. That's the point. Now, this is our main player, the asymmetric VBS state for spin 1. This is the definition in terms of the equation. So here you have this asymmetric valence bonds, simple tensor product, and I symmetrize this to get a state with spin 1. So again, these black dots are spin 1/2. We have this asymmetric valence bond. You symmetrize to get spin 1 state. Okay, so this is a disordered state that continuously interpolates between the AKLT state and the 0 state. If psi equal 1, this is AKLT. When it's psi equal, no. If mu equal 1, this is the AKLT state. If mu equals 0, this is just the 0 state. Okay, and I have to remark that very similar state that interpolates between the 2 states was already constructed by Bachmann-Nachtergel a long time ago. But ours is sort of based on this simple valence bond picture. Okay, so now I said disordered. This is disordered, but this means that all the truncated correlation functions decay exponentially. To see this, it's easiest to go to something called matrix product representation. I'm not going to explain details, but this psi the asymmetric VBS state can be represented in this way by using matrices like this. And if you form something called transfer matrix T out of this, then you can compute many things in terms of the eigenvalues of this transfer matrix T. Okay, here's the graph of eigenvalues. And Daisuke did all these calculations. And these 2-point correlation functions are explicitly written in terms of these eigenvalues. And both of them decay exponentially in distance. Okay, so this is a disordered state. Now, as for this state, we can also show that there exists Hamiltonian H mu, whose unique gap ground state is psi mu. So this connects AKLT model and the trivial model. And this is important. Since this building block, asymmetric valence bond, is not invariant under the 3 transformations, inversion, time reversal, and Z2 cross Z2, this psi mu is not, again, also not invariant. In this is inversion. This is very simple. Everything is just flipped, and you get a different state. Okay. Now that's for spin 1. So let's construct similar state for spin 2. Now we want to have a spin 2 state. So we have 4 spin 1 halves on each side like this. So this means that we have 2 asymmetric valence bond connecting 2 neighboring sites. And in this case, I designed the model, so the state, so that these 2 arrows are pointing in the opposite directions. Okay, so this is the definition in terms of equation. This is a graphic representation of the state. And again, this is a disordered state that continuously interpolates between the AKLT and the 0 state. Again, very similar state, the state which does the same, plays the same role, was constructed by Paul Monterno, Belk, and Oshikawa back in 2012. Okay, so anyway, this is again phi AKLT for mu equal 1 and phi 0 for mu equal 0, both for spin 2. And again, this is disordered. Again, this can be shown by going to matrix product representation. Again, this is Daisuke's calculation. So you have these matrices, and this is transform matrix, big one. But you can compute all these eigenvalues very easily. Probably you don't need any computers for computing this. Okay. But anyway, this shows that this state is, again, disordered. Every truncated correlation function decay exponentially. Again, in this case too, there is Hamiltonian whose ground state is this psi mu. Okay, but here's the difference. This state is actually invariant under the 3 transformations. For example, this is inversion. So here you have this state, and you just flipped. You flip this state, and then all the arrows change their direction. So this and this are different, but there's no distinction between this state and this state. So actually, this state and this state, these are the same thing. So in this case, this state is invariant under bond-centered inversion, invariant under time reversal transformation, and also the Z2 cross Z2 transformation. Okay. So here's the summary. So we have defined a symmetric VBS state and its relation to SPT phase. So it's a disorder. The asymmetric VBS state is the disordered state that continuously interpolates between the AKLT and the trivial 0 state. And there is Hamiltonian. I already said this. And psi mu and h mu, this parent Hamiltonian and the states, both are invariant under the 3 transformation for s equal 2, but not for s equal 1. But this is consistent with the picture of SPT phases. So recall that when s equal 1, h AKLT belongs to a non-trivial SPT phase. And this means that AKLT Hamiltonian and the trivial Hamiltonian are connected. They are connected within large space, but not connected within this space with space of Hamiltonians with symmetry. So in our case, we show that these 2 are connected, but within this large space of models without any symmetry restriction. But for s equal 2, we know that the AKLT model belongs to the trivial SPT phase. This was first shown by Paul Monterno, Belk, and Oshikawa. And so in this case, AKLT Hamiltonian and trivial Hamiltonian must be connected within the space of symmetric Hamiltonians. And our example, our asymmetric VBS state provides us with a simple explicit proof of this fact. Okay. And now this is the punchline. So the main topic of this video was the difference between odd and even S. And now this is the observation about asymmetry. The asymmetric VBS state is invariant under the three transformations if the arrows on every pair of neighboring sides cancel. I mean, the directions of arrows on every pair of neighboring sides cancel. And for S equal 1, we have one asymmetric valence bond on each pair of sides. So this means that you only have one arrow, you can never cancel. And for S equal 2, you have two arrows connecting neighboring sides. So in this case, of course, you can of course choose them to pointing on the right, but you can also choose the direction of arrows like this. So in this case, directions cancel. Okay. For S equal 3, you can never cancel because there are three valence bonds, and S equal 4, you can cancel. Okay. So invariant state is possible only for even S. So this tells you why odd and even are different. You can cancel the arrows for even S. You can never cancel the arrows for odd S. Okay, so here comes the summary of the whole talk. So we define the asymmetric VBS state, and this interpolates between the AKLT and the trivial zero states. And it's disordered, and there is parent Hamiltonian. And this is the symmetry. And so this state has all the three symmetries relevant to the SPT phases, that is bond inversion symmetry and bond-centered inversion symmetry, time reversal symmetry, and the Z2 cross Z2 symmetry for spin 2. But the state does not have these symmetries for S equal 1. Okay. And these observations are consistent with the theory of SPT phases and quantum spin chains. Okay. And of course, as I said, this theory is almost complete. So there's nothing really essential that we add here, but we here provided a very intuitive, simple picture. Okay, in terms of this asymmetric valence bond, and you can diagrammatically understand the difference between odd and even S. Okay, so that's basically all, but it's also kind of fun to imagine if we had come up with this idea back in 1992 when Masaki Maekawa discovered the difference between even and odd S. Okay, so that's basically all. So if you are interested, please take a look at our paper, which I hope is not hard to read. And you can find many details and also some other interesting results. And also, if you want to learn about symmetry-protected topological phases of quantum spin chains, please go to my lecture video on this subject. And I think you will see the link somewhere here. Okay, so thank you very much for watching. Goodbye.